Hello, friends. Thank you very much. This is Thomas Wambana Kuji, and today we are going to continue from where we stopped. Remember, in my first episode, we spoke about the current, the Ohm's law. We looked into resistivity, resistance, and all that. And I promised you that in my next episode, we shall be looking at the Kirchoff's laws. So do well to subscribe. Hit the subscription button below so that whenever I upload a video, YouTube will notify you so that you'll get to learn whatever I'm sharing with you. Like I said earlier, you don't necessarily need to travel long distances to have extra classes. Be in your room, follow me, and the A1 is assured. Thank you. So today we are going to look at the Kirchhoff's laws. Now, the Kirchhoff's laws are just a set of rules that help us to analyze a closed circuit. When you have a closed circuit that is made up of so many loops and junctions, you need some set of rules. They are not quite difficult, but you just need a handful of techniques and then continuous practice, and you'll be very fine. So the Kirchhoff's laws, like I said, they are just some techniques or rules that govern us to analyze electrical circuits. And there are two. There are two basic rules. The first one, we call it the Kirchhoff's first law. Kirchhoff's first law. This law states that the sum of current entering a junction is equal to the sum of current leaving the junction. This is Kirchhoff's first law. He says the sum of currents entering a particular junction is equal to the sum of currents that are leaving that junction. Now, let me take an example. You have something like this. This is a junction. Where the trail lines have met is a junction. Now we assume that there's a current moving this way. We call it I1. And when it gets here, we have two other currents that are leaving, I2 and I3. Now, per Kirchhoff's first law, which says that the sum of currents entering a junction is the same as the sum of currents leaving the junction. Here, there's only one current that is entering the junction, and here there are two. So the sum of the currents entering the junction is just one. So I1 is equal to I2 plus I3. Very simple. It's a very simple law. The law says the sum of currents entering the junction is the same as the sum of currents that are leaving the junction. So, for example, if I have something like this, here is 5 amperes, here is 9 amperes, and here is I. And there's a find the value of I. Per the little knowledge we've already obtained from Kirchhoff's first law, we know that the sum of currents entering the junction is the same as the sum of currents leaving the junction. Therefore, the one entering is 9 amperes equal to 5 plus I. And when you do your simple mathematical algebra, you have 9 minus 5. That gives us 4 amperes. Therefore, I is equal to what? 4 amperes. Very simple. Now, we are going to look at Kirchhoff's second law. Kirchhoff's second law. All right. Let me just use, instead of cleaning here, let me leave it there for those of you who would like to revisit it as we move on. So, Kirchhoff's second law. The second law states that in a closed circuit, the sum of EMFs is equal to the sum of potential differences. Very simple. This is what Kirchoff's second law says, that if you have a closed circuit, the sum of the EMFs is equal to what the sum of potential differences. Now, from Ohm's first law, potential difference V is equal to what? IR. And EMF, we have EMF to be given as this. So if the EMFs is equal to the potential difference, then it means that EMF must also be equal to what? IR. This is basically what the law says. Now we are going to take some complicated questions involving several loops, and then we analyze it based on the knowledge we've just obtained from the Kirchoff's first law and the second law in order to navigate our way through. So I'm going to put a question on the board and then we will solve it together. Thank you. In summary, I've already spoken about the Kirchoff's laws very well, and I told you that the Kirchoff's laws are a set of rules. This is just some kind of provision I'm giving you. I told you that it's a set of rules that help us to analyze electric circuits. And the first law states that the sum of current entering a junction is the same as the sum of current leaving the junction. And the diagram is here. You have current 3 entering this junction, current 2 and current 1 are leaving in the same direction. So I3 is going to be equal to the sum of I2 and I1. So the Kirchoff's laws help us to do everything with ease. All right, thank you very much. Now we look at Kirchoff's second law. And this law states that in a closed circuit, the sum of EMFs is equal to what? The sum of potential differences, the sum of potential differences in the circuit. So if you have an electric circuit which is closed, the sum of the EMFs is equal to what? The sum of the potential differences. So sum of EMF, if you see this is sigma. Sigma means sign. Sum of EMF equal to sum of potential difference. Potential difference. Sum of PD. Bear in mind, PD is always given by I times R from the Ohm's law. Now, I'm going to give you a typical example where, in fact, let me give you, we've already solved a question here similar to this place where we have a current of 9 ohms entering and 4 ohms and then a different current we're leaving. And we did a calculation and I got the answer. Now I'm going to give you a question that involves the current entering a particular junction and then a set of EMFs and potential differences that are all found in the circuits. Then we'll use the Kirchoff's laws to analyze that question. So the question is here, find the potential difference across. Find the potential difference across the 5 ohm resistor. The 5 ohm resistor in the circuit below. In the circuit below. And this is the circuit. Very simple. A very simple circuit. We have 1 ohm resistor here. 1 ohm. We have 5 ohm and 3 ohm. Five ohms and 3 ohms. Then we have potential difference. The first potential difference is 2 volts. 2 volts. The first potential difference is 2 volts. Then the next one is 4 volts. We have 4 volts here, 4 volts, 4 volts, and then I1, I2, I3. So there's a current coming this way, this one is also coming, and this one is going this way. Two are entering the junction, one is in, so this I1, I2, I3, I3. And the direction of our circuit is like this. Very good. So a question like this is very simple. And like I said, the Kirchoff's laws are very simple. But you need to continuously practice. And you need a handful of techniques. There are some few techniques that you need to master. And then continuous practice, and you are good to go. Now let's apply the first law. The first law is here. Sum of currents entering the junction equal to sum of current leaving. Which are the currents that are entering the junction? I1, I2 are entering this junction, and I3 is leaving. Therefore, I3 is equal to I1 plus I2 from the Kirchoff's first law. Now, we are done with this. Let's just leave this equation here. You need this equation. Without this, you cannot make headways. Now, let's look at the first loop. If you look at the direction, of the arrow, it tells you that the current flows in the clockwise direction, and this one is in the anti-clockwise direction, and that's okay. Now here, our EMF is equal to 2, and the potential differences are 2 here. We have potential difference across the 1 ohm resistor, and potential difference across the 5 ohm resistor. So potential difference across the 1 ohm resistor is equal to 1 times I1. 1 times I1. Now 1 times I1 is the same as I1. But for the purpose of step-by-step process of solving the problem, let's leave the 1 there so that people will not be lost. So the potential difference across the 1 ohm resistor is 1 ohm times I1. Potential difference across the 5 ohm resistor, is equal to I3 times 5. So 5 I3. So that loop is complete. This loop is complete. And per the second law, the sum of the EMFs is equal to the sum of the potential differences. The EMF is 1, the potential differences are 2. Therefore, 2 is equal to 1 times I1 is the same as I1 plus 5I3. 5I3. But from the first law, we have I3 to give us I1 plus I2. So in the end, you have 2 is equal to I1 plus 5 into brackets I1 plus I2. And when you do this one very well, you should end up having 2 equal to I1 plus 5I1 plus 5I2. So I1 plus 5I1 is 6I1. So 2 is equal to 6I1 plus 5I2. This one I can call it equation 2. So you are done with the equation 2. Now let's come to the second loop. The second loop, the only EMF is 4. So write EMF is equal to 4 volts. The potential difference across this I3 is I2 times 3. So PD across the 3 ohm resistor is equal to 3I2. Potential difference across the 5 ohm resistor is equal to 5I3. Now, if you apply the second law, which says that the EMS, when you add them together, you should get the potential difference. Then you have 4 to be equal to 3i2 plus 5i3. But from the first equation, we have I3 to be I1 plus I2, so we fix it here. So you have 4 is equal to 3I2 plus 5 into brackets I1 plus I2. And when you do this one very well, you have 4 to be equal to 3I2 plus 5I1 plus 5I2. 3I2 plus 5I2 is 8I2. We have 4 to be equal to 8I2 plus 5I1. And this one you can call it equation 3. So now you can solve equation 3 and equation 2 simultaneously. So let me clean this one by now. Sure you've mastered it. You don't have any problem here. So let me write the two equations down. We have 2 is equal to 6I1 plus 5I2. That's the first equation. The second equation, you have 4 is equal to 5I1 plus 8I2. How do we solve this equation simultaneously? Usually, I like the elimination method. So you can multiply through the equation by 5. You can multiply this equation, the first equation, by the coefficient of the first letter, and then you multiply the second one by the coefficient of this one. So I can decide to multiply everything here by this 5, and I multiply everything here by this 6. And 5 times 2 will give me 10. Equal to 5 times 6 is 30 I1 plus 5 times I2 is 25 I2. Now 6 times 4 is 24. Equal to 6 times 5 is 30 I1 plus 6 times 8. You have 48. 48 I2. Now we can subtract this equation. We can call this equation 4 and this equation 5. So you can subtract equation 4 from equation 5. So 24 minus 10 gives us 14. 30 minus 30 is 0, so every part here disappears. 48 minus 25, you have 2, 3, I2. Divide here by 23, here by 23. 23 will cancel 23, so I2 gives us 14 over 23. And if you put this one in the calculator, I2 should be given as 0.6. I2 should be given as 0.6087 amperes. So this should give us 0.6087 amperes. That is I2. Now, how do we find I1? To get I1, you can use any of the equations we've written earlier. So since this equation looks simpler, we can use that equation where we have 2 to be equal to 6I1 plus 5I2, right? If you do this, you know your I2 to be 0.6087. So 2 is equal to 6I1 plus 5 multiplied by 0.6087. And if you do that, you have 2 to be equal to 6I1 plus 5. If you multiply 5 by 0. Okay, so let's leave it as it is. Let me do the calculation here. Okay, so this one gives us, you can still maintain this. You have 5 into like a 0.6. Or better still, if you multiply 5 by 7, you will get 35. So that gives us 5 remainder 3. 5 times 8 is 40. So 40 plus 3 is 43. 3 remainder 4. 5 times 0, 0 plus 4, you have 4. 5 times 6 is 12. So that gives us 1.2. right? So this gives us 1.2435. If you do this multiplication very well, take your time to do it, you'll get it. So we send this one to this place. You have 2 minus 1.2435. If you multiply 5 by 7, it's 35. 35. So you write remainder 3, sorry. 5 times 8 is 40, so 3, 43. Remainder 4. 5 times 0 plus 4, 40. 5 times 6 is 30. 30, so that gives us 3.0, right? Now, this one is when you multiply this by this. So now you have 2 equal to 6i1 plus 3.0435. If you send this number here, you have 2 minus 3.0435 equal to 6i1. Divide here by 6 and here by 6. 6 will cancel 6. So I1 in the end, if you put this one on your calculator, you should get I1 to be negative 0. You should get negative 0.1739 amperes. So you are done with the first one. So now you know the value of I1, you know the value of I2. We go back to the very first formula where we had I3 to be equal to I1 plus I2. So when you add these values together, I3 will give us 0. Negative 0.1739 plus 0.6087. And when you do this very well, then I3 should give you 0.4 0.43 0.4348 amperes. But the question is not finished. The question says we should calculate the potential difference across the 5 ohm resistor. And I think we've already done that here. The potential difference across the 5 ohm resistor is 5i3. So if that is the case, we clean this side. And write potential difference across the 5 ohm resistor is equal to 5i3. And this is our I3 0.4 blah blah blah. So you put it here. 5 multiplied by 0.4348. And when you do that, you should be getting 2.174. 2.174 volts, and that is the potential difference across the 5 ohm resistor. Ladies and gentlemen, thank you very much. We shall be looking at more examples so that you get yourself familiarized with some of these problems. All right, so this is the second question involving closed loops. A lot of things you can see the direction of the loop is shown inside. Very complicated. It looks complicated at first glance, but if you take your time to analyze it using the Kirchoff's rules or laws, it becomes quite simple. All right, so the Kirchoff's first law says that, in fact, this is I1. Sorry, I just wrote I. This is I1. So the question says, find the current I1, I2, and I3 in the circuit below. Now, from Kirchhoff's first law, the sum of current entering a junction is the same as the sum of currents leaving a junction. The I1 is entering, I3 and I2 are leaving. As you can see, if you decide to take this one back and then this one back and push this one forward, I1 is entering, I3 and I2 are leaving. So I1 is equal to I2 plus I3. So this one, you put it equation 1. Now, let's consider this loop. The loop here, the EMF is 4. So EMF is equal to 4. And the potential difference across 5 ohm resistor is equal to The 5 ohm resistor is I2 5. So 5 I2. And the potential difference, yeah, so basically that's all. There's no any other potential difference there. Everything is very simple. And if you look at the direction of the current, it moves just like the direction of the loop. Look at the arrow, they move this way. So everything here from negative to positive, negative to positive. So your EMF is actually 4 plus 8. Sorry. So here you add 8 to it. So the EMFs, the total EMF is 4 plus 8. This one plus this, which will give us 12. So total EMF is equal to 12. Therefore, 12 is equal to 5I2. You divide here by 5, here by 5, then I2 will give you 12 over 5. I will convert this one back to fractions for you, amperes. Now, let's come to this side. You have your EMF. Look at this EMF. The direction of the loop goes this way. But if you follow the direction of the current, it moves from the positive terminal to the negative. Meanwhile, current must always move from the negative to the positive. In that case, we negate this EMF. This one too, if you follow the direction of the current, is the same way. It goes against the direction of the loop. So we negate it. So total EMF is going to be negative 6, negative 4. And that will give us negative 10. Now the potential difference across the 7 ohms, PD across 7 ohms is equal to 7I1. Therefore, negative 10 is equal to 7I1. Divide here by 7 and here by 7. 7 will cancel 7. I1 is equal to negative 10 over 7. Now let me convert this. Let me convert this into simple terms. If you divide negative 10 by 7, you get negative 1.3. So I1 is equal to negative 1.43 amperes. And for the I2, if you convert 12 divided by 5, you should get 2.4. So I2 is equal to 2.4 amperes. Now, if you put that one into the first equation where we have I1 to be equal to I2 plus I3, we know I1 to be 1.43 is equal to I2, which is 2.4 plus I3. So if you send this one here, you have 1.43 minus 2.4 is equal to I3. And when you do this simple subtraction, you will get, yes, your I1 is negative. Sorry, so you put negative here. This is negative. So when you do that, you should be getting I3 to be negative 3.84. Negative 3.84 amperes for I3. So we've succeeded in calculating the current given the question. Very simple. So the I1 is negative 1.43, I2 is 2.4, and I3 is negative 3.84. In the next episode, I'll show you more examples. But for now, thank you very much. But don't forget to subscribe. Click the subscription button so that whenever I upload a video, YouTube will notify you. Thank you.